December 19th, 1944. The frozen roads outside Bastogne, Belgium. Major William Desobry's task force was racing north toward Noville at 55 miles per hour, the fastest any armoured column had ever moved in the history of warfare. Behind him, 4 M18 Hellcat tank destroyers from the 705th Tank Destroyer Battalion screamed down the highway, their tracks throwing up frozen mud and snow as they struggled to keep pace with what everyone said was impossible. A 20-ton tank destroyer, moving faster than most automobiles of the era. The German panzer commanders, watching from tree lines 3 miles away, couldn't believe what their field glasses were telling them. American armour moving at speeds that violated every tactical assumption they had learned during 5 years of armoured warfare. This wasn't possible. The Americans built heavy, slow machines. Their M4 Shermans plodded along at 25 miles per hour. Their M10 tank destroyers barely managed 30. But these new machines were different. They moved like predators, not prey. And inside the lead Hellcat, 22-year-old Sergeant James Morrison gripped the commander's position as his driver pushed the right radial engine to its screaming limits. Morrison had heard the jokes. The engineers said the suspension would never work. Senior officers called the whole design crazy. Even the Buick engineers who built the thing admitted it looked more like a race car than a weapon of war. Too fast to be safe, too light to survive combat, too fragile for the brutal reality of tank warfare. But right now, racing toward German panzers that outweighed his Hellcat by 15 tons and carried armour 3 times thicker, Morrison understood something the critics had missed. Speed wasn't a compromise, it was a weapon. And the suspension system everyone had mocked, that supposedly insane collection of torsion bars designed by automotive engineers who had never built a military vehicle before, was about to rewrite every rule of armoured combat. The story of how a team of Buick car designers turned tank destroyer doctrine on its head began not in a military proving ground, but in the sleek design studios of General Motors in 1941. Harley Earl, the legendary automotive designer who had transformed American car design with his vision of chrome and curves, stood in his Detroit studio, looking at sketches that seemed more appropriate for a sports car than an instrument of war. But Earl wasn't thinking about sports cars. He was thinking about a problem that had kept Lieutenant Colonel Andrew Bruce awake every night since France had fallen to German blitzkrieg tactics in the spring of 1940. How do you stop an armoured thrust when the enemy's tanks can move faster than your anti-tank guns can be repositioned? Bruce had watched from Washington as German panzer divisions rolled through Poland, Belgium, and France, with a speed that rendered traditional defensive doctrine obsolete. American military planners had assumed that anti-tank warfare would resemble the static trench fighting of the Great War. Field guns positioned in prepared positions, waiting for enemy armour to advance into kill zones. But the Germans had shown that modern armoured warfare wasn't about positions. It was about movement. The panzers didn't advance in predictable lines toward prepared defences. They found gaps, exploited weakness, and moved so quickly that anti-tank guns were still being repositioned when German infantry arrived to capture them. Bruce needed something that could match the speed of a panzer attack, something that could race to threatened sectors and establish killing zones before enemy armour arrived. The army had tried improvised solutions. The M3 gun motor carriage mounted a 75mm gun on a half-track. The M6 gun motor carriage bolted a 37mm anti-tank gun to the bed of a 3/4-ton Dodge truck. Both designs shared a fatal flaw. They were makeshift weapons mounted on vehicles never designed for combat. The half-track offered no protection for its crew. The truck version turned over if the gun was fired at the wrong angle. When Bruce visited the North American Aviation Facility in 1942 to inspect the M10 Wolverine, he found a more serious attempt at a solution. The M10 was built on a Sherman tank chassis and mounted a powerful 3-inch gun in an open-topped turret. It was reliable, well-armoured, and completely inadequate for Bruce's vision of mobile tank warfare. The M10 weighed 30 tons. Its top speed was 30 miles per hour on good roads, maybe 20 cross-country. German panzer divisions could sustain speeds of 25 miles per hour across varied terrain. The mathematics were brutal and simple. The M10 couldn't respond quickly enough to blunt a German armoured thrust. By the time M10 units received word of a panzer attack and moved into position, the German armour would have already broken through. Bruce needed something faster, not incrementally faster, dramatically faster, fast enough to reach threatened sectors before the German armour arrived, fast enough to choose engagement positions instead of being forced to fight wherever the panzers found them. This required a radical departure from every principle of armoured vehicle design that American engineers had learned over 2 decades of tank development. The conventional wisdom was gospel. Armour protection came first, mobility came second, firepower came third. But Bruce's combat analysis showed that in mobile warfare, that hierarchy was backwards. An armoured vehicle that arrived too late to engage enemy tanks was useless, regardless of how much armour it carried. Bruce's vision was revolutionary in its simplicity. Build a tank destroyer so fast it could outrun anything on the battlefield. Give it a gun powerful enough to kill German tanks, and accept armour protection that was barely adequate, because speed would be its real defence. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The engineering establishment at the Ordnance Department treated Bruce's proposal with the dismissive skepticism usually reserved for perpetual motion machines. Senior engineers explained with patient condescension why his concept violated fundamental laws of military vehicle design. Colonel Thomas Nixon, who had overseen tank development since 1938, laid out the problems during a contentious meeting at the Ordnance Department's Detroit office in March 1942. A vehicle light enough to achieve the speeds Bruce wanted would need armour so thin it could be penetrated by German machine guns, not just anti-tank weapons. The suspension system required to handle high-speed operation across rough terrain didn't exist. The American automotive industry had no experience building military suspensions capable of supporting a gun turret at speeds exceeding 50 miles per hour. The Wright R 975 radial engine Bruce wanted to use generated enough power, but coupling it to a transmission that could handle extreme torque loads while maintaining reliability had never been accomplished. Nixon concluded his presentation with numbers that seemed to prove Bruce's concept was fantasy. To achieve 50 miles per hour with a 20-ton vehicle, the power-to-weight ratio would need to reach 20 horsepower per ton. The Sherman tank managed 13. The M10 tank destroyer achieved 12. Reaching 20 would require either a much lighter vehicle or a much more powerful engine, and both options created problems that appeared insurmountable. But Bruce had found allies in unexpected places. General James Doolittle, fresh from his legendary raid on Tokyo, understood the value of unconventional thinking. Doolittle had led 16 B-25 bombers off at the deck of an aircraft carrier, a mission that every aviation expert had declared impossible. He recognized in Bruce's tank destroyer proposal the same kind of calculated risk that had made the Tokyo raid successful. When Doolittle visited the Ordnance Department in April 1942, he brought a perspective shaped by years of aviation engineering. Aircraft designers routinely made trade-offs between speed, range, and payload that would horrify tank engineers. A bomber sacrificed armour protection to carry more fuel and weapons. A fighter traded endurance for manoeuvrability. Why couldn't a tank destroyer trade armour for speed? The answer, Doolittle suggested, lay not in military engineering but in the American automotive industry. Detroit had spent decades perfecting the art of making vehicles go fast. While Army engineers worried about armour thickness and gun stabilization, automotive engineers at General Motors, Ford, and Chrysler had been solving problems of weight, distribution, suspension geometry, and power transmission for an industry that measured success in acceleration times and top speeds. Doolittle's advocacy opened doors that had been closed to Bruce's radical ideas. In May 1942, the Ordnance Department authorized Buick to begin preliminary design work on what would become the T-70 tank destroyer prototype. The contract came with strict performance requirements, Top speed of at least 50 miles per hour on paved roads. Cross-country speed of 35 miles per hour across terrain that would limit a Sherman to 15. A 76mm gun capable of penetrating German tank armour at 1,000 yards. And a complete vehicle weight not to exceed 20 tons. Harley Earl's design studio received the specifications with a mixture of excitement and trepidation. Earl had revolutionized American automotive design with his belief that cars should be sculpture in motion. His team had created the Cadillac tail fin, the Corvette's flowing lines, and dozens of design innovations that made General Motors the largest automobile manufacturer in the world. But Earl had never designed a weapon. His expertise lay in making cars beautiful and fast, not lethal. The challenge fascinated him. A tank destroyer was fundamentally an automotive problem wrapped in military requirements. It needed suspension that could handle extreme loads at high speeds. It required weight distribution that kept the vehicle stable during rapid maneuvers. It demanded cooling systems that could dissipate heat from both the engine and the gun during sustained combat operations. These were automotive engineering problems, and Earl's team included some of the most talented automotive engineers in America. They approached the project with fresh eyes, unburdened by the assumptions that constrained military vehicle designers. Where Army engineers saw a tank that needed to go faster, Earl's team saw a race car that needed to carry a gun. The distinction was profound. A tank designer started with armor protection and worked backwards, adding engine power to overcome the weight penalty. Earl's team started with speed as the primary requirement and worked forward, adding only enough armor to protect the crew from shell fragments and small arms fire. The first major decision was suspension. Traditional military vehicles used either the vertical volute spring suspension, pioneered on the Sherman tank, or the Christie suspension, with its large road wheels and independent suspension arms. Both designs worked adequately at speeds below 30 miles per hour, but became violently unstable at higher velocities. The Sherman's suspension bounced so severely at 40 miles per hour that crews couldn't maintain visual contact with targets. The Christie suspension, while better at speed, created maintenance nightmares because its complex linkages were exposed to combat damage. Earl's team looked to European automotive design for inspiration. Porsche and Mercedes-Benz had been experimenting with torsion bar suspension systems that used the twisting resistance of metal bars to absorb shock loads. The system was elegant in its simplicity. Long steel bars ran longitudinally through the vehicle hull, one end attached to the hull structure, the other end connected to a lever arm that moved the road wheels. When a wheel encountered an obstacle, it rotated the lever arm, which twisted the torsion bar. The bar's resistance to twisting absorbed the shock and returned the wheel to its normal position. The beauty of torsion bar suspension lay in its characteristics at high speed. Unlike coil springs or leaf springs, which could oscillate violently when compressed repeatedly, torsion bars damped vibrations naturally. The twisting motion dissipated energy as heat within the metal structure, preventing the kind of resonant oscillations that made other suspensions unstable at speed. But torsion bar suspension had never been used on an American military vehicle. The manufacturing process was complex and expensive. Each bar had to be heat-treated to achieve the right balance of strength and flexibility. The mounting points required precision machining to prevent stress concentrations that could lead to catastrophic failure, and the geometry of the lever arms needed to be calculated precisely to provide appropriate suspension travel without allowing the road wheels to contact the hull during extreme movements. Major Samuel Barnes, the Ordnance Department liaison, assigned to oversee Buick's work, expressed serious reservations when Earl's team presented their suspension proposal in July 1942. The Germans used torsion bars, Barnes pointed out during a tense meeting at Buick's engineering facility. We've examined captured Panzer IIIs and Panzer IVs. The suspension is sophisticated, but it requires manufacturing precision that German industry can achieve because they've been building these systems for years. Our factories don't have that experience. The bars will break under combat loads, the mounting points will crack, and when the suspension fails in the middle of a battle, American tankers will die. Earl's chief engineer, Robert Lund, had anticipated this objection. Lund had spent 3 months working with metallurgists at General Motors Research Laboratories in Warren, Michigan, developing a heat treatment process that would give American-made torsion bars the strength and flexibility needed for high-speed combat operations. The breakthrough came from an unexpected source: the steel used in automotive drive shafts. Drive shafts absorbed tremendous twisting forces during acceleration and deceleration. The metallurgy that made drive shafts reliable could be adapted to create torsion bars that would survive the brutal punishment of cross-country operation at high speed. Lund's team had manufactured prototype torsion bars and subjected them to accelerated life testing that simulated 10,000 miles of rough terrain travel. The bars not only survived, they showed wear characteristics superior to the leaf springs used on the Sherman tank. The torsion bar design had another advantage that appealed to Bruce's vision of rapid deployment. The bars ran inside the hull, protected from combat damage. A Sherman's vertical volute springs were external and vulnerable to shell fragments and small arms fire. Damaged springs could immobilize a Sherman, requiring field workshops and replacement parts. A torsion bar system, once installed, was virtually maintenance-free for the life of the vehicle. The second major challenge was the transmission. The Wright R975 engine generated 400 horsepower, more than enough to propel a 20-ton vehicle at high speeds. But transmitting that power to the tracks while allowing the driver to control the vehicle required a transmission system far more sophisticated than anything in the American military inventory. Traditional tank transmissions were manually operated with multiple gear ratios selected by the driver. The M4 Sherman used a 5-speed transmission that required double clutching for smooth shifts. Experienced drivers could execute gear changes quickly, but the process was never smooth and became nearly impossible during combat when the tank was pitching violently over rough terrain. High-speed operation demanded something better. Buick's solution was revolutionary. They adapted an automatic transmission design that General Motors had been developing for luxury automobiles. The Hydra-matic transmission used hydraulic pressure to control gear shifts, eliminating the need for manual clutch operation and allowing seamless power delivery even during gear changes. Adapting Hydra-matic for military use required extensive modifications. The transmission had to handle torque loads far exceeding anything a passenger car would experience. It needed to operate reliably in temperature extremes, from -20 degrees in a European winter to 130 degrees in the North African desert, and it had to be simple enough that minimally trained mechanics could repair it in field conditions. The resulting design, designated the Torque-matic transmission, incorporated 4 forward speeds and 1 reverse. The driver controlled the vehicle using 2 steering levers and a throttle pedal. Shifting between gears occurred automatically based on vehicle speed and engine load, allowing the driver to concentrate on controlling direction rather than managing the engine. Major Barnes remained skeptical. Automatic transmissions were unproven technology even in civilian automobiles. Asking them to perform reliably in combat vehicles seemed wildly optimistic, but General Motors had been producing Hydra-matic transmissions for Oldsmobile and Cadillac since 1940. They had logged millions of miles in customer hands with reliability that exceeded manual transmissions. Technology worked. The question was whether it could be adapted to military requirements. The first T-70 prototype emerged from Buick's Flint, Michigan facility in April 1943. It looked unlike any armored vehicle that had ever rolled off an American production line. Low and sleek, with an open-topped turret that gave it the appearance of a race car more than a weapon of war. The armored hull was barely tall enough to contain the 3-man crew seated in the turret. The glacis plate sloped at aggressive angles that would deflect small arms fire, but offered minimal protection against anti-tank weapons. The 5 road wheels on each side were smaller and more numerous than those on a Sherman, distributing weight more evenly and providing a smoother ride. The Wright R975 engine was mounted at the rear, separated from the crew compartment by a firewall that isolated them from engine heat and noise. The Torque-matic transmission sat directly behind the driver's position at the sustieper, front of the hull, providing short, efficient drive shafts to the front-mounted drive sprockets. But it was the suspension that drew immediate attention from the Army test engineers who gathered at General Motors' Milford Proving Ground in late April to witness the first test runs. The torsion bars were invisible, hidden inside the hull structure, but their effect was dramatically visible. When the T-70 accelerated across the test track, it remained level and stable, with none of the pitching and bouncing that characterized other tracked vehicles at speed. When it traversed rough terrain at 30 miles per hour, faster than any Sherman had ever dared attempt, the suspension absorbed impacts smoothly, keeping the hull level and the gun on target. The test driver, Sergeant Carl Thompson, had been driving Shermans for 18 months. His first impression of the T-70 was disorienting. "This doesn't feel like a tank," Thompson reported after the initial test runs. "It feels like driving a car. A very fast, very heavy car with tracks instead of wheels. But you can see where you're going. The suspension keeps everything stable, and the automatic transmission means you can focus on steering instead of shifting gears." The performance numbers exceeded even Bruce's optimistic projections. Top speed on the banked oval track at Milford reached 57 miles per hour, faster than most American automobiles of that era. Cross-country speed across the Proving Ground's rough terrain sections averaged 38 miles per hour, more than double what a Sherman could sustain. Acceleration from 0 to 30 miles per hour took just 14 seconds, compared to 28 seconds for the M10 tank destroyer. The vision that Lieutenant Colonel Andrew Bruce had championed for 3 years was becoming reality. An armoured vehicle that could outrun anything on the battlefield. A tank destroyer that could race to threatened sectors and establish killing zones before German panzers arrived. A weapon system built on the heretical idea that speed was more valuable than armour. But proving the concept in controlled tests at a proving ground was one thing. Convincing skeptical army officers that these principles would work in the chaos and violence of actual combat would require demonstrations far more dramatic than anything that could be staged in Michigan. The real test would come in the frozen forests of Belgium, on icy roads where German Tiger and Panther tanks were massing for what would become the largest armoured battle on the Western Front. And the men of the 704th and 705 Tank Destroyer Battalions, who had trained for months on these radical new machines, would have to prove that everything the critics said was impossible could actually win battles. The 704th Tank Destroyer Battalion received their first production M18 Hellcats in June 1943 at Camp Hood, Texas. The unit had been training for 6 months on the M3 gun motor carriage, essentially a 75mm gun mounted in the cargo bed of an M3 half-track. The transition to the Hellcat represented such a dramatic leap in capability that crews initially treated the new vehicles with cautious suspicion. Sergeant Henry Romano, a gun commander in C Company, expressed the skepticism that pervaded the battalion when he first examined his assigned Hellcat in the harsh Texas sunlight. "This is what they expect us to take against Tigers?" Romano asked his crew. "The armour's so thin you can see light through it in places. The turrets open to the sky. And they want us to drive this thing at 50 miles per hour toward German tanks that weigh twice as much and have guns that can kill us from 2 miles away." Romano's concerns reflected orthodox tank destroyer doctrine. Since 1942, American tank destroyer units had been taught that survivability came from careful positioning, effective camouflage, and disciplined fire control. You found a good hull-down position, you waited for German tanks to expose themselves, and you killed them before they identified your location. Speed was useful for getting into position, but once combat began, you became static. The M18 represented a completely different philosophy. Its thin armour meant that any German tank gun could penetrate it at any range. Its open turret exposed the crew to artillery fragments and small arms fire. Its high speed and agile handling suggested tactics that violated everything Romano had learned about tank destroyer operations. Captain Thomas Evans, commanding C Company of the 704th, understood the psychological challenge his crews faced. Evans had attended the Armoured Force School at Fort Knox and studied German panzer tactics in exhaustive detail. He recognized that the M18's design pushed American tank destroyer doctrine in a direction that would require crews to completely relearn their approach to combat. During training exercises at Camp Hood in July and August 1943, Evans developed tactics specifically designed to exploit the M18's unique capabilities. Instead of static defensive positions, he taught his crews to think in terms of mobile engagement zones. The Hellcat's speed allowed them to establish positions, engage enemy armor, and relocate before German tanks could return effective fire. The key was movement. The 704th spent hundreds of hours practicing what Evans called shoot and scoot tactics. A platoon would race to a position, fire 2 or 3 rounds, then immediately displace to a new location hundreds of yards away. The Torquematic transmission made this possible in ways that would have been impossible with manual transmissions. Drivers could accelerate, maneuver, and position the vehicle without the delays and jerky movements that came with clutching and shifting. The torsion bar suspension meant that gunners could maintain sight pictures even while the vehicle was moving at high speed, something no other American armored vehicle could accomplish. Major Samuel Barnes visited Camp Hood in September to observe the 704th's training progress. What he saw challenged his skepticism about the M18's combat viability. During a live-fire exercise against simulated enemy positions, C Company's M18S raced across 3 miles of Texas scrubland at speeds exceeding 40 miles per hour. Established firing positions, engaged targets with startling accuracy, and relocated before opposing forces could respond. The entire engagement lasted less than 10 minutes. A comparable exercise using M10 tank destroyers would have required 30 minutes to cover the same distance and would have left the vehicles stationary and vulnerable during most of that time. But Barnes remained concerned about one critical aspect of the M18's performance. The open-topped turret that gave crews excellent visibility also left them exposed to overhead threats. Artillery airbursts, mortar, fragments, even hand grenades could disable or kill the crew without damaging the vehicle itself. And in close terrain, particularly in European forests and villages, enemy infantry could approach close enough to drop grenades into the fighting compartment. Evans acknowledged the vulnerability but argued that tactics could mitigate the risk. M18S would operate with infantry support in close terrain. In open country, their speed would keep them far enough from enemy positions to make infantry attacks impractical, and the excellent visibility provided by the open turret more than compensated for the exposure, because crews could identify threats and respond faster than commanders trapped in closed fighting compartments. The first combat test of these theories came not in France but in Italy, where 5 T-70 prototypes were shipped in May 1944 for evaluation by the 894th Tank Destroyer Battalion during the Anzio breakout. The results were mixed and illuminating. Lieutenant Robert Hayes commanded the reconnaissance company that received 3 of the prototype M18S. Hayes used the vehicle's speed to conduct deep reconnaissance patrols that previous tank destroyers couldn't attempt. The Hellcats could sprint ahead of advancing infantry, identify German positions, and withdraw before enemy forces could establish anti-tank defences. But the Italian terrain, narrow mountain roads winding through ancient villages, limited the M18's greatest advantage. In terrain where speeds rarely exceeded 20 miles per hour, the Hellcat offered no practical advantage over slower tank destroyers, and the thin armour proved catastrophic when German 88mm anti-tank guns engaged the vehicles in the restricted visibility of village fighting. 2 of the 3 prototype M18S were destroyed in a single engagement near Cisterna on May 23rd. The after-action reports highlighted what would become a recurring theme in M18 operations. In open, terrain with good visibility, the Hellcat's speed and agility made it a formidable tank killer. In close terrain or restricted visibility, the thin armour and open turret became severe liabilities that no amount of speed could overcome. These mixed results from Italy influenced the deployment planning for M18 units in France. General Omar Bradley, commanding 1st Army, refused to convert any of his tank destroyer battalions to the M18, preferring to wait for the more heavily armoured M36 tank destroyer with its 90mm gun. But General George Patton, commanding 3rd Army, recognised the M18's potential for the kind of fast-moving warfare he favoured. Patton requested that the three M18 equipped battalions being shipped to Europe, the 603rd, 704th, and 705th, all be assigned to Third Army. The request was approved in early July 1944. The 704th Tank Destroyer Battalion landed at Utah Beach on July 31, 1944, equipped with 36 M18 Hellcats. The unit was immediately assigned to support Third Army's breakout from Normandy during Operation Cobra. The terrain in Normandy presented challenges similar to Italy. The bocage country, small fields enclosed by ancient hedgerows, limited visibility and restricted movement. The M18's speed advantage disappeared in terrain where engagement ranges rarely exceeded 300 yards. But as Third Army broke out of the bocage and entered open country in eastern France, the Hellcat finally found terrain where its capabilities could shine. The Battle of Aracourt in September 1944 became the M18's defining moment. The 704th Tank Destroyer Battalion, attached to 4th Armoured Division, faced elements of the German 5th Panzer Army, attempting to halt Third Army's advance toward the German border. The engagement demonstrated everything that Lieutenant Colonel Bruce had envisioned when he conceived the fast tank destroyer concept. On September 19th, Lieutenant Edwin Leiper led a platoon of 4 M18s from C Company to establish positions near Rechicourt-la-Petite, a village on the road to Moncourt. Dawn fog reduced visibility to less than 100 feet, conditions that normally favored defensive operations. German commanders assumed that American forces would remain stationary in the poor visibility, waiting for the fog to lift before attempting movement. Leiper made a different calculation. The fog worked both ways. German tanks couldn't see M18s moving through the murk any better than Americans could see German armor. And the Hellcat's speed meant that Leiper could reposition his platoon multiple times during the engagement, creating the impression of a much larger force. As Leiper's platoon moved into position near the village, he spotted the muzzle of a German tank emerging from the fog less than 100 feet away. The range was so close that the usual advantages of American optics and fire control systems meant nothing. This would be decided by whoever could identify targets faster and fire more rapidly. Leiper's gunner, Corporal James Morrison, later said that the engagement felt more like a brawl than a battle. Tanks appeared out of the fog at ranges where you couldn't miss. The question was whether you saw them before they saw you, and whether your gun could reload faster than theirs. The M18's open turret proved decisive. Leiper could stand in the commander's position with his head above the turret ring, giving him visibility that German commanders trapped in closed fighting compartments couldn't match. He identified targets, designated them to his gunner, and directed his driver to new positions, all while maintaining awareness of the tactical situation that was impossible from inside a closed turret. In the first 5 minutes of combat, Leiper's platoon knocked out 5 Panther tanks from the 113th Panzer Brigade, losing 1 M18 to a German round that penetrated the thin side armour. But the remaining 3 M18s continued fighting, using their speed to appear and disappear in the fog, engaging German tanks from unexpected angles. The Germans, conditioned to fighting against static American defences, couldn't adjust to an enemy that refused to remain in position. By the time the fog lifted 2 hours later, Leiper's platoon had destroyed 10 German tanks while losing 2 M18s. More importantly, the engagement had stalled the German attack, buying time for 4th Armoured Division to establish defensive positions that would contain the 5th Panzer Army's offensive. Over the next 3 days, the Battle of Aracourt developed into a major armoured engagement involving hundreds of tanks on both sides. The 704th Tank Destroyer Battalion's 3 companies employed the shoot-and-scoot tactics they had practiced in Texas, using the M18's speed to establish ambush positions, engage German armour, and relocate before German tanks could return effective fire. The results validated everything Captain Evans had taught his crews. By September 22nd, when the battle ended, the 704th had destroyed 39 German tanks, including 15 Panthers and 2 Tigers, at the cost of 4 M18s destroyed and 3 damaged. The kill ratio was extraordinary by any standard, But even more significant was the fact that the battalion had operated offensively throughout the engagement, using mobility to dictate the terms of combat rather than accepting positions forced upon them by German attacks. Major General Manton Eddy, commanding 12 Corps, sent a congratulatory message to the 704th that captured the significance of their achievement. Your battalion has demonstrated that speed and firepower, properly employed, can substitute for armor protection. You have changed the way we think about tank destroyer operations. But the greatest test of the M18's capabilities was still to come, in frozen forests where German armor would mass for Hitler's last desperate gamble in the West. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German offensive that exploded through the Ardennes on December 16, 1944, caught American forces completely by surprise. Hitler had massed 3 armies, 28 divisions, including 10 panzer and panzer grenadier divisions, for an attack designed to split the Allied armies, capture the vital port of Antwerp, and force a negotiated peace in the West. The German plan relied on speed and surprise. Panzer columns would punch through weak American positions in the Ardennes, advance rapidly on narrow roads through the forested terrain, and reach the Meuse River before Allied forces could establish defensive positions. The key to stopping the German offensive would be controlling the road network. In the Ardennes, armies moved on roads. The forested terrain and steep valleys made cross-country movement nearly impossible, particularly in the winter conditions that gripped the region in December. Control the road junctions, and you controlled the German advance. The town of Bastogne sat at a critical crossroads where 7 major highways converged. Whoever controlled Bastogne controlled movement throughout the southern Ardennes. Both sides recognized this immediately. On December 18th, as the extent of the German offensive became clear, General Dwight Eisenhower ordered elements of the 101st Airborne Division to rush to Bastogne and hold the town at all costs. But the 101st, recovering from heavy casualties during Operation Market Garden, needed support. They needed armor, artillery, and critically, something fast enough to blunt German panzer attacks before the lightly armed paratroopers were overwhelmed. Major William Desobry commanded Combat Command B of the 10th Armored Division. On the evening of December 18th, his task force received orders to move immediately to Noville, a small village 4 miles north of Bastogne, and establish a blocking position that would prevent German armor from reaching the critical road junction. Desobry had a mixed force, 1 company of M4 Sherman tanks, 1 company of armored infantry, some self-propelled artillery, and 4 M18 Hellcats from the 705 Tank Destroyer Battalion. The distance from 10th Armored Division's positions to Noville was approximately 40 miles. Under normal conditions, an armoured column could cover that distance in 3 to 4 hours. But these weren't normal conditions. The roads were icy, visibility was poor, and German forces were moving throughout the region. Speed was critical. If Desobry's task force didn't reach Noville before German armour, the blocking position would be impossible to establish. Lieutenant Colonel Clifford Templeton, commanding the 705 Tank Destroyer Battalion, made the decision that would demonstrate the M18's unique capability. His 4 Hellcats would lead Desobry's column, racing ahead at maximum speed to secure Noville before German forces could occupy the village. If they encountered German armour en route, the M18 Sev's speed would allow them to break contact and find alternate routes. The run to Noville became legendary in tank destroyer lore. Sergeant James Morrison, commanding the lead M18, pushed his vehicle to 55 miles per hour on the frozen highway, faster than the posted speed limit for civilian automobiles, even in peacetime. Behind him, the other 3 Hellcats struggled to maintain formation at speeds that would have torn the tracks off a Sherman tank. The Torque-matic transmission handled the brutal acceleration and deceleration cycles flawlessly. The torsion bar suspension absorbed the impacts from frozen ruts and patches of ice without throwing the vehicles off course. And the crews, exposed in, their open-topped turrets to sub-zero temperatures and 70-mile-per-hour wind chill, endured conditions that would have been impossible in closed fighting compartments, where engine heat at least provided some warmth. Morrison later described the journey as the most terrifying experience of his military service. We were racing through enemy-controlled territory at speeds where a single mechanical failure or a patch of ice in the wrong place would have killed us all. Every curve in the road could have hidden a German roadblock. Every bridge could have been wired for demolition. But stopping wasn't an option. If we didn't get to Noville first, the Germans would own that road junction, and Bastogne would fall. The 4 M18s reached Noville at 11 p.m. on December 19th, nearly an hour before Desobry's main force. The village was empty. The M18 crews established defensive positions covering the northern approaches and waited for their infantry support to arrive. When Desobry, Shermans and armoured infantry reached Noville shortly after midnight, they found the Hellcats already in position, their crews shivering in the sub-zero temperatures but ready for combat. The German 2nd Panzer Division attacked Noville at first light on December 20th. What followed was 48 hours of some of the most intense armoured combat on the Western Front. The Germans had numbers and firepower. The 2nd Panzer Division included over 100 tanks, including Panthers and Panzer IVs, supported by mechanized infantry and artillery. Desobry's task force had perhaps 30 armoured vehicles total, including the 4 M18s. The Germans had tactical doctrine that emphasized massed attacks with armoured formations advancing in mutually supporting groups. American forces had terrain that channeled German attacks onto a few usable roads, and tank destroyers that could engage from positions the Germans couldn't predict. The battle developed into a deadly game of hide-and-seek. German tanks would advance down the icy roads toward Noville, and M18s would engage from unexpected positions, knock out lead vehicles to create roadblocks, then relocate before German forces could respond. The Hellcat's speed allowed tactics that would have been impossible with slower tank destroyers. Morrison's M18 would establish a firing position, engage German tanks at ranges around 1,000 yards, fire 3 or 4 rounds, then race to a new location a quarter-mile away. To the Germans, it appeared that American forces had far more anti-tank weapons than actually existed, because the same M18 would engage from multiple positions in quick succession. The torsion bar suspension proved its worth in conditions that would have immobilized other vehicles. The frozen ground and icy roads created traction challenges for all armoured vehicles, but the M18's lighter weight and sophisticated suspension allowed it to maintain control at speeds where Shermans would have slid off roads or torn their tracks. The open turret, which seemed like a fatal vulnerability in warm weather combat, provided advantages in the Ardennes. The crews could hear approaching vehicles before they appeared, giving precious seconds of warning. They could identify targets through the fog and snow that reduced visibility to a few hundred yards, and they could maintain situational awareness that closed turret commanders couldn't match. But the thin armour took its toll. One M18 was destroyed on the morning of December 20th, when a German Panther's 75mm round penetrated the front glacis at close range, killing the entire crew instantly. Another Hellcat was disabled by artillery fire that wounded the commander and loader, leaving the vehicle combat ineffective even though it could still move. By the afternoon of December 20th, only 2 M18s remained operational in Noville. But those 2 Hellcats, supported by Desobry's Shermans and the paratroopers from 506th Parachute Infantry Regiment who had reinforced the position, held off repeated German attacks throughout the day and night. The engagement became a battle of attrition. German forces had numbers, but American forces had positions and, increasingly, artillery support as more units reached Bastogne. Every German attack channeled onto the icy roads leading into Noville, where American anti-tank weapons waited in ambush. By the evening of December 21st, the tactical situation had stabilized. The 2nd Panzer Division had been fought to a standstill north of Bastogne, losing 30 tanks and suffering between 500 and 1,000 casualties. The Americans had held Noville long enough to establish the Bastogne perimeter, the defensive ring that would contain the German offensive for the next month. Team Desobry had lost roughly half its armoured vehicles, including 2 M18s destroyed and 1 damaged beyond repair. But the mission had succeeded. The road junction remained in American hands, and the German timetable for reaching the Meuse River had been irreparably disrupted. Lieutenant Colonel Templeton's after-action report captured the significance of the M18's performance at Noville. The high-speed transit to Noville could not have been accomplished with any other armoured vehicle in the American inventory. The M18's mobility during the subsequent defensive battle allowed us to create the impression of a much larger anti-tank force, which appears to have influenced German tactical decisions. The casualties we suffered reflect the vehicle's light armour protection, but the casualties we inflicted demonstrate that speed and firepower, properly employed, can achieve results that heavier vehicles cannot duplicate. The broader Battle of Bastogne continued through Christmas and into January 1945, with the 705 Tank Destroyer Battalion playing crucial roles throughout the siege. On Christmas Day, when the German 15th Panzer Grenadier Division attacked American positions with 18 Panzer IV tanks, M18 SES from the 705, destroyed 3 Panthers in a close-range engagement that lasted less than 10 minutes, breaking up the German assault before it could penetrate American lines. Throughout the siege, the 705 Tank Destroyer Battalion destroyed approximately 40 German tanks while losing only 6 M18s to enemy action. The exchange ratio was remarkable, but not unique. Similar patterns emerged wherever M18 units fought during the winter of 1944-45. The thin armour meant that any hit from a German tank gun would likely penetrate, but the speed and mobility meant that German tanks had difficulty getting clean shots at M18s that refused to remain static. By January 1945, as the German offensive collapsed and Allied forces went back on the offensive, the M18 Hellcat had proven its worth beyond any doubt. It wasn't the tank destroyer that orthodox doctrine had envisioned. It couldn't slug it out with Tigers and Panthers in a static gunnery duel. Its thin armour made it vulnerable to virtually any anti-tank weapon on the battlefield. But in the hands of well-trained crews who understood how to exploit speed and mobility, the Hellcat transformed tank destroyer operations from defensive reaction to offensive action. The engineers who said the suspension wouldn't work had been wrong. The torsion bars handled punishment that would have destroyed conventional suspension systems. The officers who said automatic transmissions were too unreliable for combat had been wrong. The Torque-matic transmission proved more durable than manual transmissions in vehicles that endured far less stress. The critics who said that thin armour made the M18 a death trap had been partly right. The Hellcat was vulnerable, but vulnerability could be managed through tactics and training in ways that the critics hadn't imagined. The M18's combat record spoke for itself. Kills claimed totaled 526 enemy armoured vehicles, 498 in Europe, 17 in Italy, and 11 in the Pacific. The overall kill-to-loss ratio was 2.4 to 1, the highest of any American armoured fighting vehicle in World War II. But statistics didn't capture the real significance of the M18's achievement. What mattered was that a team of automotive designers who had never built a military vehicle before had challenged orthodox thinking and created something revolutionary. Harley Earl's design studio had taken the speed and handling characteristics that made American automobiles the envy of the world and adapted them to create the fastest tracked armoured vehicle ever built. The torsion bar suspension that Buick engineers developed became standard on American tanks for the next 40 years. The M48 Patton, the M60, and the M1 Abrams all used torsion bar suspension derived from the principles pioneered on the M18. The automatic transmission technology that seemed so radical in 1943 became ubiquitous in modern armoured vehicles. Contemporary tanks use far more sophisticated transmissions, but the basic principle that drivers shouldn't have to manage gear changes during combat was proven on the frozen roads outside Bastogne. Most fundamentally, the M18 demonstrated that innovation could come from unexpected places. The automotive industry, dismissed by military engineers as lacking relevant experience, had solved problems that the Ordnance Department couldn't crack. The genius of American manufacturing wasn't just mass production. It was the ability to apply engineering solutions from one domain to completely different challenges, and to do so with a speed and creativity that more hidebound institutions couldn't match. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.